SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today in continuation of my last lecture, today we shall solve another problem from the steam power cycle. So, the problem that we are going to solve today is on the ideal reheat Rankine cycle. So, let us first read out the problem, then we will discuss the solution procedure. It is given that a steam power plant that operates on an ideal reheat Rankine cycle between the specified pressure limits, the pressure at which reheating takes place, the total rate of heat input to the input in the boiler, and the thermal efficiency of the cycle are to be determined. Given that boiler is working at 15 megapascal, condenser pressure is 10 kilopascal and intermediate reheating pressure is 2.15 megapascal, and it is given steam temperature at the exit of the boiler is 500 degree Celsius. So, given this data set, we need to calculate the heat input to the in the boiler. So, I am underlining the quantities which we need to calculate. One is heat input to the, so this is heat input in the boiler, thermal efficiency of the cycle, these two. So, if we start solving this problem from here, it is given that ideal reheat Rankine cycle, right. So, if we try to revisit what we have discussed, reheat Rankine cycle is the modification of the Rankine cycle, because we have seen that even after having several modifications like increasing the boiler pressure, reducing the condenser pressure and superheating steam beyond the saturated vapor state, I mean all these modifications are considered essentially for the increase in the thermal efficiency of the system, but we have also discussed about several demerits associated with these modifications, and out of these three important modifications we could discuss superheating steam beyond 0.3, that is the state point at the inlet to the turbine. If we can superheat this steam, efficiency can be increased. Efficiency will not increase at the cost of the input energy to the boiler, but at times we also can increase the quality of steam at the exit of the turbine. But the issue is that the metallurgical consideration of the blade of the turbine. So, if a turbine blade material is design I mean is available which can withstand such high temperature without inviting any operational issue like generation of thermal crack, then superheating steam could be an ideal way of increasing the thermal efficiency of steam power plant. But it is because of this restriction the concept of reheat Rankine cycle came into the picture, and I am not going to discuss the detail of this, but let us first draw the schematic. So, this is cube in, I am taking that per unit mass flow of the working substance, per unit mass flow rate of the working substance, and then we have high pressure stress turbine and after it does work in the high pressure stress turbine, steam is taken to the low pressure stress turbine and eventually we are getting W out. So, this is low pressure stress turbine. And finally, from the low pressure stress turbine steam is taken to the condenser wherein heat is rejected to the media which is circulated, and then the collected condensate is pumped back to the boiler. So, this is the place wherein we need to give work energy input in the form of work. So, basically you know that this is what is the schematic depiction of the reheat Rankine cycle. Now, let us draw the TS plane, because we have seen that if we can replace if we can map the processes, if we can represent all the processes in TS plane, then we can easily calculate the energy and heat, energy interaction, either heat or work between system and the surroundings. So, basically you know that this amount of heat is added to the boiler, and at the cost of that input energy we are getting work output. So, this is not the net work output, because this is the work output we are getting from the turbine, but we also need to give some input work to the pump for its operation, for its operation. So, now we have to understand that net work is W out minus W in, and to obtain that net work we are supplying this amount of heat. So, from there we can calculate the efficiency, but only thing is if we try to recall exactly what we have discussed in the context of this course, that we have applied steady flow energy equation. So, if the steady state steady flow equation applies to all the devices which are there, we can see here that boiler, high pressure stress turbine, low pressure stress turbine, condenser and pump, then we can figure out the energy interaction between system and surroundings. So, basically if it is a work interacting device, we can easily calculate the work either added or work extracted from the system in terms of the enthalpies. Similarly, if it is a heat injecting device, whether heat is added to the system or heat is rejected from the system in terms of the enthalpies. So, let us quickly draw the TS diagram that will help us to proceed further. So, if we try to draw the TS diagram, okay. So, this is the condenser pressure. So, this is P condenser and so this is P boiler. Okay. Now, you know that this is 1 to 2. So, this is 0.1, this is 0.2. So, let us give this is 0.1, this is 0.2, then 2 to 3. So, 3 is the inlet state at the exit of the boiler, and so this is state point 3. Now, from 3 to it is given that that we have learned from previous discussion that steam is allowed to expand in the high pressure stress turbine up to an intermediate pressure, and that pressure is given 2.15 megapascal. So, let us say this is the pressure, and then it is again reheated. After doing some work, steam is taken back to the boiler and it is allowed to pass through this heating coil, wherein again upon receiving heat it is heated, and it is heated up to the temperature of the initial superheat, and then finally it is, so this is 3 to 4, 4 to 5 and 6. So, this is the TS diagram. So, what we can see, one thing which is not given in the problem statement, that is we are taking steam. So, we are what is done here, steam is allowed to go into the high pressure stress turbine. After doing some work, it is taken back to the boiler for further reheating, and it is reheated at an intermediate pressure. So, basically when steam is doing work in the high pressure stress turbine, pressure will fall. So, this expansion is allowed up to an intermediate pressure, that is 2.15 megapascal. So, that is P4 equal to P5. These 2 points are on the same pressure line, and so basically this is 0.4 and this is 0.5 and this is 0.6, right. And that it is steam is expanded up to state point 4, and then again upon receiving heat in the boiler it is reheated, but it is not given up to what temperature it is reheated. So, this is very important. If nothing is given in the problem statement, what we have learned? We have learned that usually steam is reheated up to the initial superheat temperature basically. So, you can understand 3 is the superheat temperature before it enters into the turbine. So, that reheating is continued until the temperature becomes equal to the initial superheat temperature, that is T3. So, that is very important. T3 equal to T5, that is what we have learned from the reheat Rankine cycle, right. If this reheating temperature is given, that is good, and that is well and good, but if it is not given, then you have to assume that this reheating is done up to the initial superheat temperature, that is T3, and when it enters into the low pressure stress turbine, it again expands isentropically up to the state point 6 and it does work, and finally you are getting, you understand the turbine blades in both the high pressure stage and low pressure stage turbines are connected to a common shaft. So, from there we are getting work output. So, this is what is very important, I think we have understood. Now, let us move to see the calculation steps. So, you can understand easily, we have from our previous discussion as well as the problem we have solved in the last class. Point 1 is on the saturated liquid line, and that is, this is 10 kilopascal, that is what is given. So, this is 10 kilopascal and this is 15 megapascal. So, if we go to the next slide, P 1 equal to P 6 equal to 10 kilopascal and H 1 equal to H f at 10 kilopascal, and that you can easily get it from steam table. I am not going to show the steam table today, because what you need to go? You need to go to the saturated water pressure table or temperature table. Let me tell you one thing, here pressure is given 10 kilopascal. So, we can easily calculate the enthalpy at state point 1, that is nothing but enthalpy of saturated liquid corresponding to 10 kilopascal. Instead of pressure, if temperature is given, then you also can calculate enthalpy at state point 1, which is saturated enthalpy corresponding to that temperature. So, this is very important that we can understand point 1 is on the saturated liquid line. So, we can easily calculate, and that is 191.81 kilojoule per kg, and also specific volume, that is Vf at 10 kilopascal, and that is equal to 0.00101 meter cube per kg. See, let me tell you, though it is all the processes which I have tried to show in this TS plane are not drawn at per scale, but still if you look at the TS diagram, you can see that temperature at point 2 is slightly higher than temperature at point 1. So, ideally let us here draw. So, basically this is the constant pressure line and this is the another pressure line. So, this is point 1, this is point 2. So, you can understand the temperature at point 2 is greater than temperature at point 1. The state at 1 is saturated liquid, that is again incompressible. So, we are pumping. So, we are pressurizing that liquid to increase its pressure, so to develop pressure, but this is incompressible. So, rate of volumetric dilation is 0, we cannot compress it. Even then temperature is increasing because it is because of this viscous effect, viscous dissipation. So, this is not a heat interacting device, this is a work interacting device, and that too the process which I have tried to we have seen, this process is isentropic process, you can see from this TS plane, that is reversible adiabatic process. So long as the process is reversible, entropy generation is equal to 0, and the process is not interacting with the surrounding in terms of heat. So, when water is taken to the pump and by receiving energy in terms of work, it its pressure is increased, but it is not interacting with the surroundings in terms of heat. Even then we can see a slight increase in temperature, that is because of this viscosity. So, find that we got. So, basically we can calculate that work pump, that equal to V 1 into P 2 minus P 1. So, this is VdP, it is not PdV. So, again let me discuss something, that whether the process is reversible adiabatic or the process is reversible isothermal, so long as the process is steady state steady flow process, irrespective of the process, the work done expression is VdP minus VdP, that we have discussed. So, if we try to calculate it, it is not a PdV work. So, for any process, be it reversible adiabatic, be it a reversible isothermal, the steady state steady flow work done is minus VdP. So, this is if we try to calculate 15.14 kilojoule, 15.14 kilojoule per kg, because we are trying to calculate quantities per unit mass flow rate of the working substance. So, that we have calculated. So, knowing now from this data we can calculate H2 equal to H1 plus W pump. So, that is we will be getting 191.81 plus 150 15.14 kilojoule per kg. So, this is 206.95 kilojoule per kg. Fine. As I told you that again if we apply steady state steady flow equation to several processes and I mean which are getting executed in different devices, we will be getting energy interaction, whether it is work interaction or heat interaction in terms of the enthalpies. So, we have calculated enthalpy at state point 2, we have calculated enthalpy at state point 1. So, essentially if we can calculate enthalpy at several state points, then everything we can calculate. Fine. So, next target should be to calculate enthalpy at state point 3, state point 4, 5 and 6. So, now coming to state point 3. State point 3. So, this point is T3 is given 500 degree Celsius, P3 is given 15 megapascal. See, again we can find it from stream table that at that pressure what is Tg. If Tg corresponding to 15 megapascal is less than T3, then definitely T3 will be in the superheated regime. So, basically Tg at 15 megapascal we have to calculate from steam table. If we find that Tg at 15 megapascal is equal to T3 what is given, then that point will lie on the saturated vapor line, but if T3 is greater than Tg, then point 3 will be on the in the superheated regime. Okay. So, now if it is in the superheated regime, why I am telling this is very intuitive, but I am telling because if we know that the point 3 is in the superheated regime, by looking at the superheated steam table at that pressure we can calculate enthalpy and that we will be getting 3310.8 kilojoule per kg. And also we have to calculate entropy and that is 6.3480 kilojoule per kg Kelvin. If you look at steam table, you will find Tg at 15 MPa is less than T3. It implies T3 the point 3 is in the superheated regime and T3 you can calculate by looking at the superheated steam table. So, not only H3 and S3 you can calculate from the superheated steam table. So, I am writing from superheated table. Okay. So, we have also calculated S3. Now, why we need to take the information about entropy at that point. If we go back to the previous slide, you can see that process 3 to 4, this process is isentropic process. Now, question is, we need to calculate enthalpy at all points. So, we have calculated enthalpy at point 3, we have to calculate enthalpy at state point 4. What we know? We know P 4, because this expansion process takes place up to an intermediate pressure, that is 2.15 megapascal. So, this 4 and 5, since these 2 points are on the same pressure line, naturally P 4 equal to P 5 equal to 2.15 megapascal. What we have seen from the state postulate, because if we try to place this particular state point in TS plane, we also need to know another important intensive independent properties. So, now we have calculated entropy at state point 3 from the process that we have mapped in TS plane. The process 3 to 4 is isentropic process. So, S 4 also will be equal to S 3. We know already P 4. So, we know P 4 from the process, we can see that S 4 will be equal to S 3. So, we can easily get S 4 as well. So, knowing S 4 and P 4, we can calculate H 4. By knowing only P 4, we cannot calculate H 4. Okay. So, what we can do? So, let us go to state point 4. So, let us write process 3 to 4 is an isentropic process, and S 4 will be equal to S 3, and that is 6.3480 kilojoule per kg Kelvin, right, and P 4 equal to given, that is 2.15 megapascal. Now, let me tell you one important point. What we can do next? We know the pressure. So, again we can go to the superheated table. Initially what we can do? We can go to the saturated water pressure table, right. By looking at the saturated water pressure table at that pressure, if we try to find out what is Sg. So, I am telling you the procedure steps. So, basically at this pressure, if we try to find out what is Sg, that is entropy of the saturated vapor. If we find that the entropy S 4 is greater than Sg, there is no doubt that 0.4 will be in the superheated regime. Let me tell you once again. See, we have drawn it. In fact, I have drawn it without knowing whether 0.4 will be in the superheated regime or 0.4 will lie on the saturated vapor line. We had no clue before to place this particular state point in TS plane, but now time has come. By how? Because we know pressure. So, at that pressure, if we try to find out the saturated entropy from the steam table, even by looking at the saturated water steam table, if we calculate what is Sg, and if this S 4 is higher than Sg, then we can ascertain that 0.4 should be in the superheated regime. So, step is to check Sg at 2.15 megapascal. If S 4 is greater than Sg, then 0.4 will be in the superheated regime. right. It is seen because I have drawn it correctly. So, S4 is greater than Sg and this is in the superheated regime. Okay. Now, you know that if we know S4, then we also can calculate H4, and this H4 is 2817.3 kilojoule per kg. So, this is H4. Let me tell you one important another one important point. If the case is like this, 0.4 is on the saturated line, then H4 should be Hg corresponding to that pressure. Since 0.4 is in the superheated regime, we can directly calculate it from the superheated table. A case may be when 0.4 will be inside the vapor dome, because it all depends on the designer who is designing the turbine, depending on the requirement of the system. So, if 0.4 lies inside the vapor dome, then how can we calculate enthalpy at that point? So, if we know that 0.4 is inside the vapor dome, then I am telling you one case. If 0.4 is inside the dome, then S4 will be equal to SF plus X4 SFG, and in that case you know the total entropy at 0.4 because you got it from S3, SF and SFG that you need to calculate the pressure at which the 0.4 is defined. So, this is at 2.15 megapascal, this is at the in fact I should not write 2.15 megapascal, I will write at P4 at P4. So, this is basically I am discussing if the case is like this, right. If the case is like this, we have to calculate quality first at state point 4. Once we calculate quality at state point 4, we can then go to calculate enthalpy. H4 will be equal to Hf at P4 plus X4 into Hfg. Now, we have already calculated X4. So, this is the way by which we can calculate, by how we can calculate the enthalpy at state point 4. The common sense is, you know, this if we allow expansion, rather if you continue expansion in the first stage or high pressure stage turbine up to that point, which is 4, and if 0.4 is inside the vapor dome, then you know that again there will be some phase change heat transfer, then again it would be heated in the superheated regime. So, it is not advisable to design in such a way that 0.4 would be inside the vapor dome. You may think why, from the thermal from the of course thermal efficiency, from the consideration of the thermal efficiency of the plant. So, I am telling the best design would be not to allow expansion in the high pressure stage turbine to go up to 4, and 4 should be inside the vapor dome. Okay. So, we have calculated H4. So, if I mark H4, this is also calculated, H3 we have also calculated. So, we have calculated enthalpy up to state point 4. Next is H5. H5 it is again important. So, if we go to state point, state point 5. So, you know P4 equal to P5 equal to 2.15 megapascal. Okay. So, this is given. Now, what I was talking about few minutes back, that only one property is not good enough to give you another properties from steam table until and unless you know at least another one property. So, what we need is another one property. So, we need to go back to the problem statement. You know that this is given. So, that means steam is taken back to the boiler and it is reheated again up to the initial superheat temperature, that is T3. So, that means T5 equal to T3 equal to 500 degree Celsius. Now, again you can look at superheated table. What we can do? We can find out the temperature at this pressure, what is Tg. If Tg is less than this T5, then 0.5 will be in the superheated region. So, from the superheated table, let me write the value. So, basically P5 H5 is 3466.61 kilojoule per kg. So, what we can do, at that pressure we can find out what is Tg, and from knowing Tg, we can see if Tg is less than T5, then definitely H5, I mean 0.5 will be in the superheated region, and we can go to the superheated table to calculate H5. So, ideally we also have calculated H5. Next is H6. So, state point 6, and you know that state point 6 is process 5 to 6 is an isentropic process. So, what we can do here, we also can calculate what will be S5, because S6 should be equal to S5, right, and S6 equal to S5, that we can calculate. There are two ways. What we can do? We can calculate S5. We can, by calculating S5, we also can calculate S6, because that S6 will be equal to S5. Now, if we go to the TS plane, we can see the point 6 is inside the vapor dome. So, that S6 will be equal to SF plus X6 into SFG. SF and SFG that we know from, because that we can calculate because we know the condenser pressure 10 kilopascal, right, that way you can do. So, let me write now, that equal to S5 plus X6 into SFG, and that is at 10 kilopascal, right. So, we can calculate S5 from the steam table. Since the process is isentropic process, S6 should be equal to S5, and S6 is nothing but SF at 10 kilopascal equal to X6 into SFG, and if we calculate, that S should be equal to S6 equal to 0.6492 plus X6 into 7.4996, and this S6 equal to 7.3988, right. From there we can calculate x 6 equal to 0.9, right. So, this is 7.3998 kilojoule per kg Kelvin, right. So, this will come here. Okay. Now, since we have calculated x 6, we also can calculate what would be the h 6. So, h 6 will be equal to h 1 at 10 kilopascal plus x 6 into h f g at 10 kilopascal, and if we plug in the value, that is 191.81 that we have calculated very in the beginning, because when we have calculated pump work, we have calculated that is 191.81. So, let me write here, and this is 0.9 into this is 2392.1. So, this quantity is kilojoule per kg. It is very important to mention here that always you should write the unit of all these quantities. So, this is coming as 2344.7 kilojoule per kg. So, finally, we have also calculated H 6. So, now calculating enthalpy at every state point, next what we can do, we can easily calculate the rate of heat supply. So, rate of heat supply if we calculate per unit mass flow rate of the working substance, that is what we have considered in this analysis, we can calculate H 3 minus H 2 plus H 5 minus H 4. Why? So, if we go back here, so we are supplying H 3 minus H 2 initially, and again steam is entering at state point 4 and leaving at state point 5. So, H 4 H 3 minus H 2 plus H 4 minus H 5 H 5 minus H 4. So, the amount of heat that should be added to the boiler is equal to H 3 minus H 2 plus the amount of heat required to increase the temperature of steam when it comes from high pressure stress turbine and goes to the low pressure stress turbine, that is H 5 minus H 4. So, if we calculate here, and then we will be getting, that is I mean we can we know that H 3 equal to 3310.8 H 3 minus H 2 is 206.95 plus H 5 3466.161 minus 2817.2, that is the. So, this is the unit should be kilojoule per kg. Okay. So, this is per unit mass flow rate of the working substance, that is rate of heat supply. So, this is one part, and another part is thermal efficiency. So, that is 1 minus Q out divided by Q in. Okay. So, this is this is Q in. So, this is Q in, and what about Q out? Q out equal to H 6 minus H 1. So, if we go back to the previous slide, so H 6 minus H 1, that is the Q out from the condenser. Okay. So, this quantity is coming as 2344 0.7 minus 191.81. So, this is again kilojoule per kg. If we try to plug in the value of Q in and Q out in this expression, we are getting efficiency equal to 0.428. So, that means efficiency is 42.8%. So, if we try to summarize, we have seen that in this problem we need to calculate the heat input and the thermal efficiency, but to calculate thermal efficiency you also had to calculate heat output. So, what we did, in addition to the heat input, we also had to calculate heat rejection from the system, and calculating these two quantities we have quantified the thermal efficiency and it is coming as 42.8%. So, if we try to summarize, we have taken this example, we have discussed several issues while solving the problem, and finally, I would like to discuss one important point, that you know the efficiency is 42.8%, that is even not 50%. So, ideally efficiency should be higher, but what we can see from this calculation is that though we have taken, I mean even though we have calculated efficiency is equal to 42.8%, but let me tell you, we have taken a few assumptions like isentropic process, but in reality it is very difficult to achieve these processes in practice. What will happen? All these processes will invite thermodynamic irreversibility, and thermodynamic irreversibility will disallow the system to run at the best exergetic efficiency. So, that means efficiency will be even less in real life, in real practice. Why this is happening? So, that means to run the system, though we need to supply energy in the form of heat, but the work output that we are getting is less, and it is because of this reason we have seen that heat is termed as low grade energy, while work is termed as the high grade energy in thermodynamics. And second point is that the amount of heat that we have added, the amount of energy that we have added to the system in the form of heat, a part of that is converted to the useful work. Remaining energy is getting lost from the system to the surroundings. We need to do it, otherwise we will not be able to run the system in a cyclic manner, and that is what is the restriction imposed by the second law of thermodynamics. Okay, so, with this I stop here today, and we shall continue our discussion in the next class. Thank you.